foundations of mathematics is the study of the logical and philosophical basis of mathematics, or, in a broader sense, the mathematical investigation of what underlies the philosophical theories concerning the nature of mathematics. In this latter sense, the distinction between foundations of mathematics and philosophy of mathematics turns out to be quite vague. Foundations of mathematics can be conceived as the study of the basic mathematical concepts and how they form hierarchies of more complex structures and concepts, especially the fundamentally important structures that form the language of mathematics, also called meta-mathematical concepts, with an eye to the philosophical aspects and the unity of mathematics. The search for foundations of mathematics is a central question of the philosophy of mathematics. The abstract nature of mathematical objects presents special philosophical challenges. The foundations of mathematics as a whole does not aim to contain the foundations of every mathematical topic. Generally, the foundations of a field of study refers to a more or less systematic analysis of its most basic or fundamental concepts, its conceptual unity and its natural ordering or hierarchy of concepts, which may help to connect it with the rest of human knowledge. The development, emergence and clarification of the foundations can come late in the history of a field, and may not be viewed by everyone as its most interesting part. Mathematics always played a special role in scientific thought, serving since ancient times as a model of truth and rigor for rational inquiry, and giving tools or even a foundation for other sciences. Mathematics' many developments towards higher abstractions in the 19th century brought new challenges and paradoxes, urging for a deeper and more systematic examination of the nature and criteria of mathematical truth, as well as a unification of the diverse branches of mathematics into a coherent whole. The systematic search for the foundations of mathematics started at the end of the 19th century and formed a new mathematical discipline called mathematical logic, with strong links to theoretical computer science. It went through a series of crises with paradoxical results, until the discoveries stabilized during the 20th century as a large and coherent body of mathematical knowledge with several aspects or components, whose detailed properties and possible variants are still an active research field. Its high level of technical sophistication inspired many philosophers to conjecture that it can serve as a model or pattern for the foundations of other sciences. Historical context. Ancient Greek mathematics. While the practice of mathematics had previously developed in other civilizations, special interest in its theoretical and foundational aspects was clearly evident in the work of the ancient Greeks. Early Greek philosophers disputed as to which is more basic, arithmetic or geometry. Zeno of Ella produced 4 paradoxes that seem to show the impossibility of change. The Pythagorean school of mathematics originally insisted that only natural and rational numbers exist. The discovery of the irrationality of square root 2, the ratio of the diagonal of a square to its side, was a shock to them which they only reluctantly accepted. The discrepancy between rationals and reals was finally resolved by Eudoxus of Cnidus, a student of Plato, who reduced the comparison of irrational ratios to comparisons of multiples, thus anticipating the definition of real numbers by Richard Dedekind. In the Posterior Analytics, Aristotle laid down the axiomatic method for organizing a field of knowledge logically by means of primitive concepts, axioms, postulates, definitions, and theorems. Aristotle took a majority of his examples for this from arithmetic and from geometry. This method reached its high point with Euclid's Elements, a treatise on mathematics structured with very high standards of rigor. Euclid justifies each proposition by a demonstration in the form of chains of syllogisms. Aristotle's syllogistic logic, together with the axiomatic method exemplified by Euclid's Elements, are recognized as scientific achievements of ancient Greece. Platonism as a traditional philosophy of mathematics starting from the end of the 19th century A Platonist view of mathematics became common among practicing mathematicians. The concept saw, as Platonists would have it, the objects of mathematics are abstract and remote from everyday perceptual experience. Geometrical figures are conceived as idealities to be distinguished from effective drawings and shapes of objects, and numbers are not confused with the counting of concrete objects. Their existence and nature present special philosophical challenges. How do mathematical objects differ from their concrete representation? Are they located in their representation, or in our minds, or somewhere else? How can we know them? The ancient Greek philosophers took such questions very seriously. Indeed, many of their general philosophical discussions were carried on with extensive reference to geometry and arithmetic. Plato insisted that mathematical objects, like other Platonic ideas, must be perfectly abstract and have a separate, non-material kind of existence, in a world of mathematical objects independent of humans. He believed that the truths about these objects also exist independently of the human mind, but is discovered by humans. In the Meno, Plato's teacher Socrates asserts that it is possible to come to know this truth by a process akin to memory retrieval. Above the gateway to Plato's academy appeared a famous inscription, "Let no one who is ignorant of geometry enter here." In this way Plato indicated his high opinion of geometry. He regarded geometry as the first essential in the training of philosophers, because of its abstract character. This philosophy of Platonist mathematical realism is shared by many mathematicians. It can be argued that Platonism somehow comes as a necessary assumption underlying any mathematical work. In this view, the laws of nature and the laws of mathematics have a similar status, and the effectiveness ceases to be unreasonable. Not our axioms, but the very real world of mathematical objects forms the foundation. Aristotle dissected and rejected this view in his Metaphysics. These questions provide much fuel for philosophical analysis and debate. Middle Ages and Renaissance. For over 2,000 years, Euclid's Elements stood as a perfectly solid foundation for mathematics, as its methodology of rational exploration guided mathematicians, philosophers, and scientists well into the 19th century. The Middle Ages saw a dispute over the ontological status of the universals. Realism asserted their existence independently of perception. Conceptualism asserted their existence within the mind only. Nominalism denied either, only seeing universals as names of collections of individual objects. René Descartes published La Géométrie, aimed at reducing geometry to algebra by means of coordinate systems, giving algebra a more foundational role. Descartes' book became famous after 1649 and paved the way to infinitesimal calculus. Isaac Newton in England and Leibniz in Germany independently developed the infinitesimal calculus based on heuristic methods greatly efficient, but direly lacking rigorous justifications. Leibniz even went on to explicitly describe infinitesimals as actual, infinitely small numbers. Leibniz also worked on formal logic, but most of his writings on it remained unpublished until 1903. The Protestant philosopher George Berkeley, in his campaign against the religious implications of Newtonian mechanics, wrote a pamphlet on the lack of rational justifications of infinitesimal calculus. They are neither finite quantities, nor quantities infinitely small, nor yet nothing. May we not call them the ghosts of departed quantities? Then mathematics developed very rapidly and successfully in physical applications, but with little attention to logical foundations. 19th century. In the 19th century, mathematics became increasingly abstract. Concerns about logical gaps and inconsistencies in different fields led to the development of axiomatic systems. Real analysis. Cauchy started the project of formulating and proving the theorems of infinitesimal calculus in a rigorous manner, rejecting the heuristic principle of the generality of algebra exploited by earlier authors. In his 1821 work called The Analyze, he defines infinitely small quantities in terms of decreasing sequences that converge to zero, which he then used to define continuity. But he did not formalize his notion of convergence. The modern definition of limit and continuous functions was first developed by Bolzano in 1817, but remained relatively unknown. It gives a rigorous foundation of infinitesimal calculus based on the set of real numbers, arguably resolving the Zeno paradoxes and Berkeley's arguments. Mathematicians such as Carl Weierstrass discovered pathological functions such as continuous, nowhere differentiable functions. Previous conceptions of a function as a rule for computation, or a smooth graph, were no longer adequate. Weierstrass began to advocate the arithmetization of analysis, to axiomatize analysis using properties of the natural numbers. In 1858, Dedekind proposed a definition of the real numbers as cuts of rational numbers. This reduction of real numbers and continuous functions in terms of rational numbers and thus of natural numbers was later integrated by Cantor in his set theory, and axiomatized in terms of second-order arithmetic by Hilbert and Bernays. Group theory for the first time. The limits of mathematics were explored. Niels Henrik Abel, a Norwegian, and Évariste de Galois, a Frenchman, investigated the solutions of various polynomial equations, and proved that there is no general algebraic solution to equations of degree greater than 4. With these concepts, Pierre Wantzel proved that straight edge and compass alone cannot trisect an arbitrary angle nor double a cube. In 1882, Lindemann, building on the work of Hermite, showed that a straight edge and compass quadrature of the circle was also impossible by proving that pi is a transcendental number. Mathematicians had vainly attempted to solve all of these problems since the time of the ancient Greeks. Abel and Galois's works opened the way for the developments of group theory and abstract algebra. Concepts of vector spaces emerged from the conception of barycentric coordinates by Mobius in 1827, to the modern definition of vector spaces and linear maps by Peano in 1888. Geometry was no more limited to 3 dimensions. These concepts did not generalize numbers but combined notions of functions in sets which were not yet formalized, breaking away from familiar mathematical objects. Non-Euclidean geometries. After many failed attempts to derive the parallel postulate from other axioms, the study of the still hypothetical hyperbolic geometry by Johann Heinrich Lambert led him to introduce the hyperbolic functions and compute the area of a hyperbolic triangle. Then the Russian mathematician Nikolai Lobachevsky established in 1826 the coherence of this geometry, in parallel with the Hungarian mathematician János Bolyai in 1832, and with Gauss. Later in the 19th century, the German mathematician Bernhard Riemann developed elliptic geometry, another non-Euclidean geometry where no parallel can be found and the sum of angles in a triangle is more than 180 degrees. It was proved consistent by defining point to mean a pair of antipodal points on a fixed sphere and line to mean a great circle on the sphere. At that time, the main method for proving the consistency of a set of axioms was to provide a model for it. Projective geometry. One of the traps in a deductive system is circular reasoning, a problem that seemed to befall projective geometry until it was resolved by Carl von Stout, as explained by Russian historians. In the mid-19th century there was an acrimonious controversy between the proponents of synthetic and analytic methods in projective geometry, the two sides accusing each other of mixing projective and metric concepts. Indeed, the basic concept that is applied in the synthetic presentation of projective geometry, the cross ratio of 4 points of a line, was introduced through consideration of the lengths of intervals. The purely geometric approach of von Stout was based on the complete quadrilateral to express the relation of projective harmonic conjugates. Then he created a means of expressing the familiar numeric properties with his algebra of throws. English language versions of this process of deducing the properties of a field can be found in either the book by Oswald Veblen and John Young, Projective Geometry, or more recently in John Stilwell's Four Pillars of Geometry. Stilwell writes on page 120, projective geometry is simpler than algebra in a certain sense, because we use only 5 geometric axioms to derive the 9 field axioms. The algebra of throws is commonly seen as a feature of cross ratios since students ordinarily rely upon numbers without worry about their basis. However, cross-ratio calculations use metric features of geometry, features not admitted by purists. For instance, in 1961 Coxeter wrote Introduction to Geometry without mention of cross-ratio. Boolean algebra and logic attempts of formal treatment of mathematics had started with Leibniz and Lambert, and continued with works by algebraists such as George Peacock. Systematic mathematical treatments of logic came with the British mathematician George Boole, who devised an algebra that soon evolved into what is now called Boolean algebra, in which the only numbers were 0 and 1 and logical combinations or operations similar to the addition and multiplication of integers. Also De Morgan publishes his laws. Logic becomes a branch of mathematics. Boolean algebra is the starting point of mathematical logic and has important applications in computer science. Charles Sanders Peirce built upon the work of Boole to develop a logical system for relations and quantifiers, which he published in several papers from 1870 to 1885. The German mathematician Gottlob Frege presented an independent development of logic with quantifiers in his Begriffsschrift published in 1879, a work generally considered as marking a turning point in the history of logic. He exposed deficiencies in Aristotle's logic, and pointed out the 3 expected properties of a mathematical theory: consistency, impossibility to prove contradictory statements, completeness. Any statement is either provable or refutable. Decidability. There is a decision procedure to test any statement in the theory. He then showed in Grundgesetze der Arithmetik how arithmetic could be formalized in his new logic. Frege's work was popularized by Bertrand Russell near the turn of the century, but Frege's two-dimensional notation had no success. Popular notations were for universal and for existential quantifiers, combing from Giuseppe Peano and William Ernest Johnson until the symbol was introduced by Gerhard Ganson in 1935 and became canonical in the 1960s. From 1890 to 1905, Ernst Schroeder published Vorlesungen über die Algebra der Logik in 3 volumes. This work summarized and extended the work of Boole, De Morgan, and Peirce, and was a comprehensive reference to symbolic logic as it was understood at the end of the 19th century. Peano arithmetic. The formalization of arithmetic as an axiomatic theory started with Peirce in 1881 and continued with Richard Dedekind and Giuseppe Peano in 1888. This was still her second-order axiomatization, as concerns for expressing theories in first-order logic were not yet understood. In Dedekind's work, this approach appears as completely characterizing natural numbers and providing recursive definitions of addition and multiplication from the successor function and mathematical induction.